situations here. The first one, this is kind of like nice case that we just drew the picture for, right? We have the nice smooth isoquants. So if there's an interior solution I should say, solution is interior. With no kinks in the isoquants.
Yeah. Yeah.
Then the following condition holds.
There has to be one specific call. I was saying we use math.
The slope
to be specific one.
of the isoquant equals the slope of the isocost line, like we just saw in that picture, right? And remember, the slope of the isoquant is the technical rate of substitution at x1, x2 star equals the slope
Also calculating
of the isocost line, which we just saw. The slope of the isocost line is this negative W1 over W2. Remember, the technical rate of substitution is the minus of the marginal product of input 1 at the optimal amount of input 1 over the marginal product of input 2 at their optimal amounts equals negative W1 over W2. Now, so this looks very similar to that marginal rate of substitution equals the price ratio, right? I mean, the negative of the price ratio, the slope of our budget constraint equals the slope of our indifference curve. Here, we just have the slope of the isoquant is equal to the slope of the isocost line. But remember, you can only use that condition if, this is only going to be true at the optimal if we have no kinks in our budget constraint. We have this nice interior solution. And so this would be one equation and one unknown, and then we have the other equation, which is f of x1, x2 equals some level of production. And we're going to have two equations and two unknowns. So we can solve for x1 star and x2 star and figure out the cost function. We can solve this for x1 star, x2 star, and can find this cost function that we've been talking about, which is a function of W1, W2, and Y. Now, in general, x1 and x2 star are going to be functions of the amount of output as well as the input prices. So really, maybe it's better to put x1 star and x2 star is x1, it's a function of W1, W2, and Y. And x2 star is a function of W1, W2, and Y. So this is how we could approach solving this minimization problem using calculus if we get them calculate the marginal products by taking the derivative with respect to the production function of good 1 over the derivative production function with respect to good 2 and setting it equal to the ratio of input prices or the slope of the isocost line. But again, we can only use kind of these two equations and two unknowns if we have an interior solution with no kinks. So it's kind of one category of problems. We've kind of seen when we can't use this. So if we have a boundary solution, I'll erase that as if we have one. Or kinks, or kinky, or kinks, maybe I'll just say in the isoquant, then this condition won't hold. And we need to kind of attack those problems or solve those problems a little bit differently. So let's quickly erase this board and kind of talk about two different cases. One with perfect substitutes, where we're going to have a boundary solution, and one where we have kinks in the isoquants when we have those perfect complements in production, and how we can go about solving those versions of this minimization problem. But again, this method is only going to work when we have, setting the slope of the isoquant equal slope of the isoquant is only going to work when we have interior solutions with these nice, well-behaved isoquants with kind of no kinks and things like that. So when we can't, in this case, we're going to have a boundary solution. In this kind of, here we're going to specifically talk about perfect substitutes. So these inputs can be substitutable between each other. Well, let's imagine there's a 1-for-1 substitution, which means our production function might just equal something like x1 plus x2. So we could perfectly substitute between input 1 and input 2 in the production process. Here, we won't have that tangency condition, right? Because the isocost lines are straight lines, and so are the isoquants. Because of this kind of linear relationship, or because it's x1 plus x2 here, for instance, if we're looking at a production of 1, we could use one input of input 1 and 1 unit of input 2. We can use either of those to produce 1. Or any kind of combination, half of each of these inputs could also produce, if we use half of these two inputs together, we could also produce 1 output. So it's a straight line, the isoquant, which means we won't have that nice tangency condition. Here, and this is probably going to make a lot of intuitive sense here, we would use the cheaper of the two inputs, because it's a 1-to-1 here. Now, you could also have a production function that would be like x1 plus 2x2, and that would slightly change it, right? That means for every unit of input 2, we could produce 2 output, but we can only produce 1 output with 1 unit of input 1. So here, the min cost of producing y units will be either W1 times y or W2 times y, whichever is lower. So essentially, because they're substitutable in some, here it's 1-to-1, but it could be 1-to-3 or 2-to-1 or whatever. And we're just going to think about, well, what's the cheapest way to produce y units? Well, in this case, when it's 1-to-1, it's going to be whatever's cheaper, using y units of x1 to produce y units, because it's just a 1-to-1 in terms of output and input here, times the cost of input 1, or the cost of input 2 times the amount of input 2 we're using to produce y units, where in this case it's just y. Notice if it was a 2 here, we have to divide this by 2. So keep that in mind for getting a bit more general idea of how to solve these. So your cost function here, which is again a function of input prices and how much we're producing, is just going to be equal to the min of W1Y or W2Y. Well, if you can factor Y out here, which is just the min of W1, W2 times Y. Again, this is just like the simplest version. We could think of a more general one where we have like a 2 up here or a 3 over here, and that's going to slightly change our answer. Again, we're just trying to think of the cheapest way to produce Y units, and that's just going to depend on the prices. But we're going to only use, unless we have an infinite number of different production, and unless we have an infinite amount of different solutions to this minimization problem, we're only going to be using one of our inputs. We just got to figure out which of these inputs is cheapest to produce like 1 unit, and then you're just producing Y of those units, for instance. The other one, so this is like the cost function. The other one is when we have kinks in the isoquant line. And for example, we saw this. One example of this is when we have perfect complements in production. So in this kind of category of problems, we have a straight line for our isoquant line, so we don't get that tangency. And then we just need to figure out what's, we're only probably going to use one input. What's the cheapest input to use? We're only going to use that one. Here, this is like our perfect complements, just like utility, where we have those kinks in the isoquants. And if our production looks like this, well, we need to use the same number of these 2 units. Again, we can make it more general by putting a 2 here or a 1 there. It could be more general. But this is how you solve like the simplest version of this, where we're just taking the min of the number of inputs. So now if we want to produce Y units of output, we need x1 units, really, y times x1 units of input 1, and x2 units of input 2. So here, we would need y, just because of this production function. If we want to produce y units, we need y units of input 1 and y units of input 2. So these are both equal to y because of this production function, because it's just a 1-to-1 complements between the two. Now our cost function, which again is a function of the cost of each of these inputs and how much we're producing, is just going to be W1 times Y, because we need to use Y units of input 1, W2 times Y, which is the same thing as saying Y times W1 plus W2. Essentially, we need kind of one input to produce everything, and that one input is both of these inputs combined in this case, right? So the cost of producing in 1 unit of this output is just the cost of both inputs combined, and then we just multiply it by how much we're producing. All right, so those are kind of 3 categories of problems. We have the nice smooth one where we don't have any kinks, it's That means there's no kind of min argument in the production function or something like that. And we don't have corner solutions. Then we can use that tangency condition. The second kind of like category of problems is when we have this boundary solution, and that's going to happen, for example, when we have perfect substitutes. And I just picked the simplest perfect substitutes here, where it's 1 for 1. If that's true, you're just going to pick out whatever one's cheapest. But you should know how to solve this problem, even if it's like, you know, even if this was like a 2 over here or a 3 in front of the x1, how you figure out what the cost is. And finally, we have this third kind of category. We have kinks in the isoquants. Here, we need to use these, you know, an example of this is we have perfect complements, and here we need one of each kind of input to produce one output. It's the minimum number, so it's like we have these right angles in terms of our isoquants. So let's say this is, you know, output y, some general output y here for this isoquant. We're trying to figure out the isocost line that just touches that isoquant general y we're trying to solve. Well, here we know at this solution that x1 equals x2. Then we also know how much we're producing, right? We would know that we need to produce y units, so that means min x1, x2 equals y with some number, and this is how we get the solution. Up here, we just have a straight line. Let's say these are our isoquants. And let's say these are isocost lines. And so here, this is the lowest isocost, so this has a slope of W1 over W2. And these are isoquants. This is an isocost. So here, you can tell just by the slope, it's cheaper to use input 2 than input 1. And so that means we're just going to use input 2 to produce this and 0 input 1. So these just look like the categories of problems we had to solve for the utility maximization. And we couldn't always use that tangency condition. Hopefully this helps us think about these problems in different categories and how to approach them.